using implicit differentiation to differentiate inverse function. Let's do an example. Let's show the d dx of ln of x is 1 over x using the fact that d dx of e to the x is e to the x. If y equals ln of x, then e to the y equals x, and also if e to the y equals x, then y is ln of x. We are going to use that. We are going to do implicit differentiation now for e to the y equals x. We differentiate both sides. d dx of e to the y is e to the y times dy dx. d dx of x is 1. Now we are going to solve for dy dx. And we get that dy dx equals 1 over e to the y. But pay attention. E to the y is x. And we get 1 over x. Let's see what actually we were doing here. First, we write the inverse function. Then, we differentiate implicitly. And then, we were substituting. We are now going to approach this in a different way. Let's assume that the inverse function is ln of x. Obviously, if the inverse function is ln of x, then the function f(x) is e to the x. Let's now compose the two functions. F composed with the inverse of f of x is always x, but in this case, if you see, it's e to the ln of x. Now I'm going to differentiate both sides. By doing so, I don't have any y, but I only have to differentiate in both sides two functions that are only functions of x. Here, using the chain rule, I'm going to get e to the ln of x times the derivative of ln of x, which I have no idea what it is. This is what I'm looking for. On the other hand, I get d dx of x, which is 1. Now I can solve to d ln of x over dx. It is 1 over e to the ln of x, but e to the ln of x is x, and I get 1 over x. Again, I got the same thing, that d dx of ln of x is 1 over x. In general, if a function f(x) is 1 to 1 on an interval ab, then f(x) has a 1 to 1 inverse function f to the negative 1 of x on the interval ab. And we also know that the two composition f with f of negative 1 of x equals x, and the other composition f to the minus 1 f of x equals x. It means that I can actually take this and differentiate both sides. Let's see, what do I get? Here I have to use the chain rule. And here I just get d dx of x, which is 1. Let's apply the chain rule from the left side. It is the derivative of the outer function f, and we get f prime of f to the negative 1x times the derivative of the inner function, which is the derivative of f to the negative 1x. But now I can find what is the derivative of f to the minus 1x. It is 1 over f prime of f to the negative 1x. theorem. If f(x) is a one-to-one and differentiable function with an inverse function f to the negative 1x, which is also differentiable, then d dx of f to the negative 1x equals 1 over f prime of f to the negative 1x, provided obviously that f prime of f to the negative 1x is not 0. Now we're going to again do the same example, but now we want to show that d dx of ln of x is 1 over x using the theorem. F to the negative 1 of x, which means the inverse function of fx, is ln of x. And fx is e to the x. Let's now apply the theorem. F to the negative 1 of x is ln of x. And we get the d dx of ln of x equals what? Let's see. It's 1 over what? The function is e to the power of x. F prime of x is e to the x. But if you see, in the denominator here, we have f prime of f to the negative 1 of x, which means it's going to be now f prime of ln of x. F prime is e to the x, so f prime of ln of x is e to the power of ln of x, which is just x. And we get that this is just 1 over x. As you can see, it is possible to calculate the derivative of a given inverse function in 3 different ways. And this is obviously if the derivative of f to the inverse function x is not 0. The first way, which I think was the easiest way, was using implicit differentiation. The second way is a little bit more complicated, but it's almost like the first one. It's just that instead of having y, we are only going to have, in two sides of the equation, only functions of x, because f of y is also f of the inverse function. And the last way to do it was using the theorem. Example, find the derivative of the inverse function to the function fx for x cubed minus 2x at x equals 2. Pay attention, in this one, we have no idea what is the inverse function. X equals 2 is with respect to the inverse function. If x equals 2 is an x value of the inverse function, then it means that 2 is the y value of f of x. Now we have to use the theorem. We know that the function is for x cubed minus 2x, so the derivative of the function is 12x to the power of 2 minus 2. Now we have to substitute for x the inverse function. We do, and we get 1 over 12 times the inverse function to the power of 2 minus 2. I have no idea what is the inverse function, but I do not care about that because I don't need to find the derivative of the inverse function. I have to find the derivative of the inverse function at x equals 2. this is a different story, because now I know that I have to substitute 2 instead of the x, and I get that. But now I have to find out what is the value of the inverse function at x equals 2. When x equals 2 in the inverse function, then we know that 2 is the y value of f(x), so 2 equals to f(x), which is 4x cubed minus 2x. We are trying numbers, and we find out that when x equals 1, f of 1 is 2. Now it's clear that the inverse function at x equals 2 equals to 1, because we are just switching between the x's and the y's. So we are replacing the inverse function at 2 by 1, and we get 1 over 12 times 1 to the power of 2 minus 2, which is 1 over 10. In general, to find this number, we can try number or use the graph of the function f(x). Here is the graph of f of x. Because x equals to the inverse function, we have to find the value of x for which y equals 2. And after we get this point, we can figure out what is the x value.